So, hello and welcome to the second lecture in the webinar series about small angle scattering. My name is Chris Garvey as usual, and I'll be taking you through some discussions about instrumentation today. So, in today's lecture, we're going to talk about how we get the probability of scattering, whether that be neutron or X-ray, through a particular solid angle by a sample. We talk about instruments. Another way of thinking about today's lecture is, well, this is my first experiment. What do I do? So we'll talk about instrumentation, other aspects of the experiment, the samples and data reduction and normalization treated in lecture 4. So today's lecture 2, is about neutron and X-ray small angle scattering instrumentation. Divided into SACS instruments and SANS instruments. Some of these are in your own lab. Some of these are large-scale facilities. They have their particular attributes, advantages, disadvantages, and I'll also give you some feel for how the instrumentation works. So here we are again at our familiar schematic SANS instrument. We have a beam of neutrons or X-rays incident on a sample, and the beam is scattered and spread out, and we count neutrons as a function of angle. And down the bottom, we see an example that I've given before of where we've collected data from red blood cells to use that to understand the interaction between hemoglobin molecules and the red blood cell. So I'll be talking about some practical aspects of using small angle scattering instrumentation. So first thing I'm going to talk about lab SACS. Now you'll all get a chance to experience some lab SACS instrumentation during the practical sessions, and you might put these remarks in that context. So these days, usually SACS instruments in the lab have a 2D detector. Very rarely linear or point detectors. There are some old instruments around, but it's unlikely that you'll ever see these. So the advantage of the 2D detectors, of course, is that you count over a much larger solid angle, and then you can do the radial averaging for better statistics. The X-ray sources these days are also a bit of a range. Most instruments have an X-ray tube. There's a few rotating anodes around, and very few instruments are now using these metal jet sources, which have much larger fluxes than the rotating anode or the tube. I guess the practical aspect of all this is how long it takes to count, because in none of these cases you're really going to damage a sample with radiation as you might do at a synchrotron beamline. So tubes tend to have the lowest flux. The rotating anodes, which are a bit rarer, a bit higher, and the metal jet sources approach the flux of synchrotrons, but not really. Instruments tend to have a single fixed wavelength, and you might like to think of that in terms of how that affects the Q values that you're looking at. Some facilities offer different kinds of X-ray sources. Usually the samples are in glass capillaries in a vacuum, so this is to reduce the background. So there's some obvious problems with samples that are exposed to air. All the moisture gets sucked out of them, and so placing the sample in a container can be really quite a challenging feat, and you'll probably experience this when you come to the practical sessions in a few weeks' time. When data from a lab source is most normally normalized, it's used to a secondary standard, or some instruments use a counter on the beam stop. Measurement times, depending on the sample, is minutes to hours, and this is usually related to the X-ray source and there's really no possibility of beam damage. The Q min is flux and geometry dependent, so usually you can move the detector a fixed distance away from the sample, and in one sense that determines the Q min, but also as you move it further back there's less to count and the background becomes relatively higher. So if you want to get to very low Q, you probably need to go to a synchrotron source, or maybe even think about light scattering. With most instruments, there's a fixed Q range, so there's a major question. The major question that you face when you come to instrumentation is how long do you count? But again, all of these are issues that you might like to discuss when you come to do the practical session. Here we have 3 examples of lab-based sax instruments. I think the one you'll see in the practical session is related to the one on the far right hand side, but you can see the same basic construction. You have an X-ray source, then some form of collimation, and then a sample, and then at the end of a flight tube or in an evacuated tank, a detector. So in the case of the Brooker Nanostar on the left, this instrument's about 10 to 15 years old. There's a detector facing closest to us, that's that grey box. There's a flight tube. You open the sample and put it inside the grey box, which is under vacuum. And furthest away from us is the X-ray source. So between the sample grey box and the X-ray source is a collimation. The Heckes is a little bit different. It's a much shorter, more compact instrument. It has focusing optics. The sample to detector distance is not that great. And also it has a wax detector on top as well. This instrument has a really nice feature that it can do DSC runs as well as sax at the same time. The Xenox at the top right hand side is probably facing us in the best way to see everything there. So on the left hand side there's the X-ray source, the long thin tube is the collimation. There's a grey box there with some, again, samples that can be under vacuum. And the detector sits inside those grey boxes there, and in this model I believe it can move quite continuously between different sample to detector distances. So this one has quite a flexible Q range, the other two don't. I think that you can get quite a range of sample environments to go inside the grey box, but these are all very typical lab sax instruments. So in the next slide I'm just going to briefly talk about synchrotron sax. This falls into the category of large-scale facilities. So you might access through a proposal system where you write a little mini research proposal and it's reviewed by our committee, and they may or may not give you some beam time. It's usually a fairly tiring event. You may get 1 or 2 days of beam time, and that really does mean that you have 24 or 48 hours of beam time. There's a lot of synchrotron facilities around the world, and I've given you a bit of a link to have a look at a few of the ones in Europe. In general, you can use a huge range of sample environments on the sax beamline. You can just do straight solution scattering. One can put something like a rheometer, a DSC. I've stretched samples. It's really quite limited by your imagination. These beamlines tend to have very flexible, almost continuously adjustable Q ranges. That's due to the variation in the sample to detector distance, and many of them also have a tunable X-ray source, perhaps from 8 to 20 keV. The important thing is, in contrast to the lab sax beamlines, that the counting times are extremely short, so they're of the order of seconds. So in the 24 or 48 hours, even given setup time, you can make many measurements in the course of a beam time. It's also really important to remember it's very easy to make lots of bad data when you're overawed by the the amount of data that you can have. So my advice is to be extremely careful. Typically, Q-min is limited by the detector solid angle and by how far away you can move the sample from the detector, the optics in fact. Unlike lab SACs where flux is always a limitation of Q-min, well, an important limitation, you don't have so much problems. As I mentioned before, these beamlines have typically a tunable X-ray wavelength from 8 to 20 keV. Beam damage is always a problem, and one might be tempted to go to the higher energies to avoid beam damage. In some cases, it's possible to do certain kinds of contrast variation experiments with anomalous or energy-dependent SACs. If you're interested in that, you can Google it or even ask me. Generally, the data is normalized to a secondary standard, that is water. So if you have some beam time at a synchrotron, it's really important to have a serious conversation with the beamline staff, and you may need to be quite insistent on this. It's important to front up with well-prepared and characterized samples and a team that's ready for measurements overnight. As I said, it's very easy to make lots of bad data very quickly on these kinds of beamlines. The key decisions you really need to make before you do the experiment is the Q range, and that of course will be dependent on the energy or wavelength of the X-rays, and the sample detected distances or distance. Some beamlines can only accommodate one sample detector distance. Some have, like the Xenox machine that we showed recently, and SANS beamlines have almost a continuous movement of a detector in a tank. You might also like to think about what kind of environment you want to measure your synchrotron SACs in. But my firm advice is to consult with the beamline staff very clearly before you make the measurement. So just a bit more advice when you're doing these experiments, just keep in mind that you'll acquire a monumental amount of data. So be very careful about keeping a good sample records. Record the relationship between the sample and the file name that the synchrotron beamline is going to write very carefully. Make sure you have all the required backgrounds and normalization files before you leave. And this really should be part of the conversation that you have with the beamline staff before the experiment, how they do that particular, how they do those particular exercises on their beamline. It's also really good to become familiar with data reduction and actually the acquisition software as well. It's handy if you can understand these things and do them on the fly, and gives yourself the ability to evaluate the experimental data as you go along. If you have a team of a few people, maybe give one person this task to look after the beamline running, and given that you have maybe 24 or 48 hours, it's good to rotate people around different tasks once they've learnt them. It's also really quite important to evaluate the possibility of beam damage. This is always a possibility at a synchrotron. If you have enough sample, damage a sample with the beam. And that way you know what it looks like and you know how to avoid it. And my final piece of advice is, if you're doing a synchrotron experiment, make sure you get some sleep, because people who are tired don't function very well. So after the beam time, this is going to sound a bit repetitive, but you're really tired and you need to get some sleep. You probably have a lot of data, and it's good to get the data while you're there. And of course, you're familiar with the data reduction. A typical experiment will be maybe tens of gigabytes of image data. When you have the time, as soon as possible, while the experiment's still fresh in your mind, it's really good to evaluate the data quality. Sort the good from the bad. Bad data is just a waste of time. You can spend as much time evaluating and reducing data that's bad for no outcome, whereas the outcome from good data is obviously publication quality data. So what I've got in the next few slides is a few examples of some synchrotron beamlines. This is the Sachs wax beamline at the Australian synchrotron, and this photograph's a bit old. It's fairly typical of a beamline that you might encounter. There's some specs there for it. I've been talking about energy, and I thought it'd be good to put that in the context of wavelengths. And the Q range is fairly typical for this kind of beamline. So we're looking down from the synchrotron. At the back there's a detector, and between the detector and the sample is some flight tubes. So in the old days, they could move the flight tubes out and move the detector at the front, which was quite a time-consuming operation. You can see there's a track for running the various pieces of flight tubing along. Nowadays, this has been replaced with a detector in a large tank which can move continuously. There's quite a bit of room around the sample at the front of the detector tank, and they really could accommodate a large range of different kinds of sample environments on this beamline. Quite a nice beamline. Now, this beamline's a bit odd. It's not really used for Sachs mostly. I've shown it here in the Sachs configuration. And the first thing you'll notice there as you look down the synchrotron, this is the top photograph, is this very long flight tube. And in the bottom thing, we have a very small detector. This instrument, which is not really built for Sachs, has a very small detector, which of course gives you a very small solid angle and a very small Q range. So when you come to do an experiment at a synchrotron, always think about the Q range that you're going to ask. Now, rather than show you another photo of a beamline, I've shown the schematic of the ID2 beamline at the SRF. This is a really big beamline. It's highly productive, and you get really nice data on this. Without worrying too much of the details of the optics there, if you go to the sample position and see that it's about 65 meters from the undulators, and the detector itself can go back to 100 meters, so that's about 35 meters of sample to detector distance, and this means that this beamline can really go to very low Q values. So when you're thinking about the experiment that you're going to do, be aware of what kind of Q range you want, and that will come from a consideration of what kind of structures and the sizes that you're looking for, which should become second nature to you after this course. So now I'm going to talk about pinhole sands. So there's not that much difference conceptually between pinhole Sachs and pinhole sands. Is instead of X-rays, you have neutrons. And of course, the nature of neutrons mean that you're not going to damage a sample. In the past and at the moment, I think most pinhole sands are on reactor sources. But this is changing with spallation sources becoming increasingly operational. The Paul Scheer Institute, PSI, operates like a reactor actually. There's ISIS and ESS soon to become operational. On reactors, it's usually a fixed wavelength SANS instrument with the velocity selector that I showed you in the slide, and I'll probably show you again. Some use the time of flight technique, which I'll talk a little bit more about later. And mostly these time of flight SANS instruments are on spallation sources. Fixed wavelengths usually require multiple configurations for spanning the Q range. And so as I've shown you in the past, that the sample to detector distance is measured maybe 2 or 3 times depending on the Q range that you want. It's important to remember each time you move the configuration, it's going to cost you time, and the constraints on measurement time are really quite different on a reactor than, well, for neutrons in general, than for synchrotron Sachs. By contrast to the fixed wavelength instrumentation, the time of flight single instrument requires a single instrument configuration for a Q range. This means they're good for kinetics. There's some flexibility in the Q range that you can have. but generally you measure at a single configuration for an experiment. The time of acquisition for pinhole sands, as I said before, is really quite different from synchrotron sources, although they're both large facilities. It's usually of minutes to hours, so of the same time scales that you'll have for a lab-based SAX instrument. It also depends on the Q range that you're looking at, the contrast, etc. But a typical beam time allocation is 1 to 4 days, with a much less frenetic changing in samples. So on this slide, I have on the left-hand side the two SANS instruments at the ACNS in Sydney, Australia. I don't show them because they're particularly special, but because they're the two instruments that I'm more familiar with. Quokka, as I said, and I think I've shown it 2 or 3 times, is a fixed wavelength instrument. And so if you look at the front, there's a velocity selector which selects a band of wavelength from the cold source. The neutrons travel along the green line through the collimation, interact with the sample, and there's a detector in a detector vessel which can be moved almost continuously along back and forth. As I said before, a lot of modern SAX instruments, you also use this configuration, and I think the one at the in Lund also uses this approach. The instrument on the right, Bilby, is smaller. It covers an equivalent Q range in one go. It has a bank of detectors in that sort of reddish coloured tank, and importantly, when the sample is illuminated by neutrons, it's not a fixed wavelength. It's a spread of wavelengths, and you'll notice in the picture that I've drawn there in the schematic of the instrument there's some choppers. So what this means is that as well as scanning Q with angle, we also do it with wavelength at the same time. And so these choppers are able to label neutrons according to their wavelengths. So when the scattered neutrons arrive at the detector, with some fancy electronics, you can tell what wavelength they are. And so this gives this kind of instrument a much wider dynamic range for measuring in one shot than the conventional pinhole sands. Now, I'll just mention this instrument briefly. This is a U-SANS, and it's a Bonser Hart geometry. There's a few different kinds of U-SANS, and they vary in how they detect neutrons. Some of them have area detectors, some of them have point detectors, and in principle, this instrument has a point detector as well. So every point on the scattering curve is measured a point at the time, and you can see that it means that it's not so good for kinetics, because a typical measurement or a rocking curve takes 2 to 8 hours to measure. Now, for some kinetics, that's fine, but the point of this instrument is that it does allow you to get to very low values of Q, length scales of the equivalent of maybe tenths of microns. So there's some other wrinkles around this instrument, which I'll talk about a bit more in a so this is kind of a complicated slide. The main take-home messages I'd like you to take from this slide are that when you measure particularly with a SANS instrument, there's some smearing of the data. So if one considers that on a pinhole SANS, you're measuring the intensity as a function of Q or angle, if that angle is not particularly well defined, i.e. the beam is spreading out and hasn't been collimated quite perfectly, it has some effect on the scattering pattern, and that's what the central panel shows, and so it affects the effective Q resolution. And in the software that many of the data reduction packages used account for this explicitly, and we'll talk about that when we come to the practical sessions. On the left-hand side, we've shown an effective long slit smearing, and this is very typical of instruments like the Bonser Hart I showed you. Now, it is possible to treat these smearing analytical. There's some equations you can do to calculate it, And so that's often the approach to deal with these issues. I probably won't say so much more about this. So here's a Bonser Hart type SANS instrument. It's really quite small compared to the SANS instrument. The footprint of this is only a few square meters, whereas you can remember the tank of the SANS instrument was about 20 meters in length. I think that's all I'd like to say about this slide. So just to put this these two techniques into context of the length scales that you're looking at. So on the top again we have the reciprocal space range, and on the bottom we have the real space range. And so you can see that USACs and USANS maybe goes from tens of microns down to hundreds of nanometers, and SANS and SACs will typically span from maybe nanometers up to hundreds of nanometers. So just to give these instrument conversation a little bit further context, is what I've got here is data from 3 instruments. The Kookaburra USANS instrument, which is KKB, and you can see from the black dots the Q range that it spans. The data up the top is actually being de-smeared. The raw data is the empty circles, and you can see that you maybe get down to hundreds of nanometers, or even tens of nanometers in this case, which is a really good sample. The sample itself is a cubisome, so it's a particle made of lipid block copolymer particles, so there's some internal structure. So if you look at the curve for Quokka, it spans from about 0.6 down to about maybe 7 by 10 to the minus 4 reciprocal angstrom. So it has a lot wider Q range than Bilby, but this is done with 3 instrument configurations. I've shown 2 settings with Bilby. One, that's the green line, goes to a slightly lower Q than the other setting, which is a blue line, but they both differ in the measurement time. So if you absolutely need the lower Q, it's going to take you a lot longer to measure, in this case about an hour, and certainly the time of flight SANS of the type of Bilby cannot get to the same Q min as Quokka. But the thing to remember about the time of flight SANS is it's made that measurement in one shot. There's no moving around the detector while the sample is changing. So it's really quite useful for flux. Sorry, for kinetics. So how do the instruments vary? Flux, so that's measurement time. The Kookaburra data, the USANS data, takes about 6 hours to measure. The pinhole SANS instrument takes about 1.5 hours, and the two Bilby time of flight configurations take 1.5 and 2.5 hours respectively. The extra time gets you a little bit of extra lowering Q. So in conclusion, and I realise that was an awful lot of detail, but I think it's really quite useful when you start to put these observations in the context of the experiments you're doing. And don't be afraid to ask questions of instrument scientists and maybe push them outside their comfort zones a bit. So typical small angle scattering instrumentation can measure over a range of length scales determined by the instrument configuration. So how they set up the instrument determines the Q range that you're going to look at. In some cases, the Q min is determined by the flux. There's not so many neutrons or X-rays to count at very low Q. This is particularly the case for lab SACs. Detector size, if you have a big detector or a bank of detectors, or some variation in wavelengths, such as the time of flight, you get a dynamic Q range which is much larger. In the case of SANS instruments, pinhole SANS instruments on reactors, there's a change in sample to detector distance, and this takes time and has some disadvantages. It's also really good to remember that instrument time at large-scale facilities is generally fixed. you get so much time allocated and you have to make your measurements in that time. So plan things well. If you're working in a lab, on a lab source, you really have much more time to think and to be a bit more adventurous experimentally. And I think this is probably the best place to get started. Finally, instrument configurations can be optimized for a particular scientific problem. So be aware of the length scales that you want to investigate and how quickly you want to investigate them if you're interested in kinetics, and talk to the instrument scientist. I'll recommend a couple of textbooks that I think have some emphasis on instrumentation, particularly Norbert Streiberg's book on X-ray scattering of soft matter has some very useful and good practical advice on how to, in particular, do a good synchrotron X-ray experiment. But the book on neutron scattering in polymers, even if polymers aren't your thing, is really quite useful as well and has many useful observations in it. So if you haven't already attempted these exercises, I'd really suggest you do. It's going to be very helpful for you. And if you want, you can just take it a little bit further using ImageJ. Draw some model structures and do some Fourier transforms and generate some scattering curves.